Hey everybody, this is your mic check at 8 minutes. Feel free to say something in the chat if you heard me. Hey everybody, welcome to episode 12 of Goldendale Observations. It's a big show tonight because we have big subject matter on our mind. The sun is big in its importance, and it's also big in its size, at least compared to Earth. We'll be talking a little bit about the size of the sun and other stars and finding out that you have to keep that relative concept in mind because some things seem big until you compare them to others, and some things seem small until you compare them to others, etc., etc. My name is Troy Carpenter. I'm coming to you live from the new Goldendale Observatory. And this is a topic of discussion tonight that we're not foreign to. We talk about the sun all the time here at Goldendale Observatory because we do have solar telescopes, plural, and we do make good use of them when we're open. Tried to get some footage of the sun today to show you, but of course, again, clouds decided that was impossible. But I'm going to try next week again, try to get some fresh sun footage. But that being said, you're going to see lots of pictures and video footage that we shot here at Goldendale Observatory of the sun. So, as usual, before I begin, please keep in mind we are a public observatory. We exist for sake of education. Please ask questions during this presentation. Make comments too, and it will help us to tailor the show to your interest and educational needs. I hope you guys are enjoying your 2021 so far. I know that's kind of a joke statement. But I promise it's going to get better. I'm very optimistic. Maybe I'm naive to be so optimistic, but it doesn't hurt to be optimistic. So hopefully by the end of this year, we'll be getting people back in here. Who knows? I don't want to make any promises about when we're going to reopen again. But in the meantime, we're doing this, coming to you live via the miracle of high-speed internet. At least I hope you're watching with high-speed internet so you can watch in high quality. Speaking of high quality, some of this footage may impress you in its fidelity. We've come a long way in the last few decades when it comes to imaging the sun. It used to be a very difficult prospect. Now it's almost trivial. It's affordable. You can buy the equipment necessary to do it in your own backyard. It used to be that solar astronomy was limited to well-heeled individuals, colleges, research facilities, things like that. So, as usual, we'll be watching the chat for questions, and I'm going to be watching our moderated chat as well. Let me know if anything comes up. I will say, I don't see any chat right now, and I want to make sure that everything's fine. So if you guys don't mind, if someone could type one or two things in the chat, I want to make sure that we can see you, because right now I don't have anything in the chat box. I could do the show blind, but I'd prefer to have some feedback. Still don't see. Hold that thought. I'm going to try something else. Just make sure I'm not crazy. Let's see here. I'm going to open it up in a different browser. Oh, good. I see the chat. Fixed it. That's funny. So, back to business. Hello, everybody. Yes. All right. Let's start with some footage that we shot of the sun here at Goldendale Observatory, and we're going to talk about it. I have been using this particular piece of footage for years because it's just so darn good. Because on the particular day that we shot this, we had good examples of all the most famous features that one sees on the sun. As you can see, this is wiggling and moving. This is video. This is not a photograph. And this was shot back in 2014. And in that year, the sun was quite active. We're going to talk a little bit about the sun's activity cycle during this show. And you're going to learn that it ebbs and increases. And we're going to see some changes related to that cycle. You're going to learn that, for example, the last solar max was 2013. And 2014 being kind of close to that year, we had quite a lot of activity to look at. For most of the last 2 years, the sun's been extremely quiet, and so it was difficult to get footage like this, at least footage that would include so many interesting structures. Yeah, so we're going to go over the nature of all these structures you see on the surface. I already know the word flare is probably popping up in your minds, and no, that's not what that thing is. That object right there, that's not a solar flare. That's called a prominence. That's one of the types of solar phenomena that we're going to identify. So, it may impress you that we can get footage like this of the sun. I would like to go over briefly how it's possible and also cover a little bit of safety. Some of you may have attempted to image the sun before. You must be careful. You must know what you're doing. Not only because you can blind yourself, but you can also damage your equipment. If you point, for example, an unfiltered camera attached to a telescope at the sun, well, guess what? You can melt the sensor on your camera. Don't do that. That's an expensive lesson. I've never done it, but I do know people who have melted their cameras, and that's an expensive lesson indeed. Don't do it. So let's talk about it. Here is a very boring image of the sun. This is a very common image of the sun. If you were to ever attempt to look at the sun through filtration, you'll get an image like this because the type of filtration used is very common. This is known as white light filtration or continuous spectrum, and it simply entails dimming the sun for sake of safety. So the primary reason to filter the sun in this way is to make it safe to observe. Unfortunately, you lose a lot of interesting features in the process. Now here's an example of a fairly nice white light solar filter. You may have used one or seen one before. These are not expensive. This is a very nice one, like a really high quality one. This was $50. So these are not that expensive and very easy to get. Unless you wait until the last minute before a solar eclipse, then they're very difficult to get because everyone uses up the material and then they start charging outrageous prices. So, by the way, I don't recommend doing that. Never wait until the last second when it comes to observing a solar event. Get your solar filtration material ahead of time. So yeah, white light filtration, very common. This is metallized mylar. All it is mylar with an aluminum coating, which makes it very shiny. And of course, the reflectivity rejects most of the solar energy, most of, in this case, infrared and visible wavelengths, so that you can safely observe the sun. But like I said, limitations. If you've ever used eclipse goggles, those glasses, those cardboard things you get, same technology, and they can be mass-produced very cheaply. I hope you didn't pay more than a few bucks for those things, because they're literally cardboard in a little bit of mylar with aluminum coating on it. Yeah, and you could even make your own as long as you make sure the material you purchased is certified for use with solar and not just heat, for example. Okay, so if you want to get a more interesting view of the sun, we have to do something more sophisticated. We have to use a much more advanced type of filter. This filter is known as a hydrogen alpha etalon. Etalons are not filters in the traditional sense. It's not simply absorbing energy and converting it into heat or bouncing it away. This device is much more clever. It phase cancels out specific wavelengths, retaining other wavelengths of interest. These can be tuned to allow you to see the wavelengths you want to see. In this case, a hydrogen alpha etalon is tuned to 656 nanometers wavelength, which happens to be the first line of hydrogen emission spectra, and that's why we call it the hydrogen alpha line. I'll explain what that means in a second, but just be aware, this is the device we use to get images like what you're seeing. Well, let's see. Let me give you one. Like this. Notice how much more interesting the sun just became in hydrogen alpha light. Let's talk about why. I'm going to ask you guys a very basic question, and I would like a very basic answer. Don't think about it too hard. I'm going to go back to that boring picture. I want you guys to tell me why it is that the sun is bright. Someone tell me, why is the sun bright? Now, there's many correct answers to this. Give me a very basic one. Let's see if you can get it. Oh, someone asked, what are the black dots? Those are sunspots. Hold that thought. We're going to get to that. Oh, good. Someone says hot. Yeah. Look at this thing. Here's a big light bulb. Hey, let's see if you guys know. Most of the grown-ups in the room should know. What kind of light bulb is this? What do we call these? What kind of light bulb is this? It's old. This is from the 40s, actually. This is very old. Anyone know what kind of tells? Edison. Okay, well, incandescent. Very good. So incandescence is the layperson's term for black body radiation. It's the description of the luminosity produced by heat. Incandescence is not limited to visible light, of course, but in this case, when you look at sunshine, that beautiful, that glorious incandescence is a result of the sun's hot surface. The sun's surface is about 10,000 degrees Fahrenheit. And so that's hot enough to make it bright looking. Unfortunately, it's a problem because all that glare blows out fine features and details. When you attempt to image the sun in white light using proper filtration, you unfortunately lose features and only retain the one that someone already asked about, the sunspots. Now, since you just correctly told me that the sun is bright because it's hot, what do you think is different about sunspots? Someone tell me, what do you think is different about sunspots, guys? I'm watching. Cooler, yes. And I'm glad to, oh, good, good. These are all very excellent, even carefully chosen words because they ain't cold, but they are cooler. So the average surface temperature, like I said, might be about 10,000 degrees Fahrenheit. But the sunspots are much cooler, around 6,000 degrees Fahrenheit. We'll talk about why they exist and why they're cooler in a second. But I should ask this very basic question. Are they permanent? What do you guys think? Are sunspots permanent? I'm watching the chat. What do you guys think? Are sunspots permanent? No. They come and go. Sometimes you'll see many. Sometimes the sun will be covered with them when it's very active. Sometimes you'll see none whatsoever. In fact, I mentioned how the last 2 years the sun's been very quiet. It's starting to wake up now. And it was not uncommon to go weeks and weeks and weeks without seeing a single sunspot. But when the sun is very active, you might see, like I said, multiple sunspots every single day. The sun is fun because it always changes. It always looks different every single day. And I'm going to show you some videos in a few minutes that kind of prove that. Yeah, so white light filtration really only allows you to see the absence of light. So it's also good for seeing things like eclipses because something's blocking the sun, transits when a planet goes in front of the sun, and of course sunspots. But if you don't have any of those things happening, if you don't have any sunspots, if you don't have any transits, if you don't have any eclipses, and you look at the sun using white light filtration, you end up getting a white circle. Keep that in mind. You got to spend a few bucks on one of these things if you want to see more. We're going to talk more about that in a second. But I do want to go over a basic grade school science lesson really quick. What is white light? What is it? Anyone want to tell me what white light is? I know you know this. Is white a color? All colors, good. So good old Isaac Newton showed us that white light was actually all the colors that one could see combined. He proved this using prisms, made a rainbow out of the white light, then he took that rainbow, put it through another prism, and he got white light again. So, thank you, Isaac Newton. Let's go back to the more interesting image. There we go. The hydrogen alpha image reveals many features that could not be seen because of the glare of white light. And we're going to briefly show you how this thing works. So I told you about this filter. I'm actually going to make my head big for a second, just so you can see this filter up close. It is a chamber that contains many layers of glass. And these layers of glass are very, very precisely installed. The gap separating them is very deliberate. The thickness of the glass is heavily maintained during manufacture. They're also coated with certain rare earth elements. And something ingenious happens. When light from the subject enters this chamber, it bounces back and forth between the layers of glass and is delayed. But the light is delayed in a very specific amount of, for a very specific amount of time, very deliberate. Let me show you what I'm talking about. Actually, let me take my head out of there. So we have essentially our incoming wave of light. The delay inside the chamber causes it to become 180 degrees out of phase with itself. So it's out of time. It's exactly out of phase with itself. Those rays of light are transposed. And what do you think happens when you have light that is exactly opposite itself interacting? Well, it cancels out. So the etalon uses destructive interference to eliminate all wavelengths of light. But you know, eliminating all wavelengths of light is not something very difficult. You could do that with a piece of wood, or your hand in front of your face. So it's not actually the reason etalons were invented. They were not invented to block all light. They were invented to block all wavelengths of light except for those we're interested in. Now I told you this was a hydrogen alpha etalon. And I told you that it was allowing through the first line of hydrogen emission. You guys probably know, thanks to the science of spectroscopy, that all elements have their own unique spectra. So we have famous neon here with its orangey red color. Sodium, if you've ever seen high pressure sodium light bulbs and street lights, they're yellow, as you can see. Mercury has a complex spectra with many different colors. Oh, look, there's some helium. Again, complex spectra. And then here's hydrogen. Now, this is the emission spectra of hydrogen. This is the color signature, if you will, of hydrogen when you ionize it. Now, you'll notice that it has multiple colors, like we have, for example, some red, and we have some blue and some violet. And that all combines to create sort of a pretty rosy color. So here's my favorite space object, the Orion Nebula. And you can clearly see that rosy color. And that rosy color is associated with hydrogen emission. There are many objects like this in the universe, giant clouds of hydrogen. There's the Rosette Nebula, and again, look at the color. So that rosy color, that is the emission spectra of hydrogen. Now, the etalon is allowing us to see the emission spectra of hydrogen, but it's blocking everything else. I want to make sure you guys understand this before we move on. Why did we choose hydrogen? This etalon could have been tuned to any wavelength. So why did we choose that of hydrogen? What do you think? I want to make sure someone points it out, says it in the chat before I move on. Why would we invent a device, or rather in this case, they were not invented for solar astronomy, by the way, but why would we use a hydrogen alpha etalon to study the sun? What do you think? Oh, someone says there's a lot of it. I like that answer. I'm going to be kind of dumb about this on purpose. Where is there a lot of hydrogen? Someone tell me. Where is it all? Sun is mostly hydrogen. That's true. What else is mostly hydrogen? Yeah, good. What else is mostly hydrogen? Well, the answer is the entire universe. So this is the emission and absorption spectra of our galaxy. The Milky Way galaxy is a modern galaxy, so to speak. It encompasses modern ratios of heavy elements. And so it gives us a lot of insight into the modern universe's chemical enrichment by studying its spectra. And as you can see, in the modern universe, we have almost nothing but hydrogen and helium. Those two elements, hydrogen and helium, still, after over 13 billion years of cosmological nucleosynthesis, still dominate the periodic table. Most baryonic matter or ordinary matter in the universe is hydrogen and helium. Any questions about that? So, when we look at the sun or anything through a hydrogen alpha etalon, we're really seeing it for what it's made out of. But we've eliminated the glare in the case of the sun that prevents us from seeing interesting structures. I have a lot more to say, but are there any questions so far about that? Let me show you an interesting chart. I've showed you this on other shows, but it's always fascinating to talk about. Oh, yes, the sun does have sodium. Good timing, actually, my friend. So here we see the absorption spectra of a bunch of stars you've never heard of. Now, I want to explain absorption spectra. You saw emission spectra a second ago. This is the light emitted by material when it's excited to a plasma state. But now we're seeing absorption. So the colorful rainbows you see, this is actually the light of incandescence. This is the continuous spectra of all these stars. And again, these are not famous stars. Look at their names. But notice that there's these little dark lines. Those are absorption lines. Now, the spectra of our sun would look something like this one here in the middle. And Ed here asked about the sun having sodium. If I zoom in a bit, you might be surprised to find that yes, it sure does. So, let's see. Right here, this double yellow line is sodium absorption. As you can see, most of these stars have sodium. But not this one. Look at that. Interesting. Not this one either. That's very significant. There's something profound about these stars. They're not all from the same generation. A lot of people don't know this, but the universe contains 3 generations of stars. And you can tell what generation a star belongs to by measuring its metallicity. Metallicity is the term for the chemical enrichment of a star. As the universe ages, it becomes more and more chemically enriched because stars literally manufacture heavy elements from lighter ones. So, you can tell how much material a given star has inherited from the previous generations by studying its spectra. Our sun is considered metal rich because our sun is a member of the youngest generation, but it is a middle-aged member. So we call it an intermediate population 1 star. Now, if that 1 confuses you, be aware that we name stellar generations backwards. So the first generation of stars born immediately after the Big Bang are called population 3, and the very first stars that we see in the universe, very difficult to study, tend to have almost no metals at all when we study them. But stars that are born recently air quotes, like our sun, or even more recent stars like Sirius or the star Vega in the sky, these stars are rich in heavy elements because they were born into a universe with lots of material. So yeah, our population 1 star is actually a member of the youngest, the sun, and there's also some population 2 stars on this chart. So let's zoom in again. Let's compare. Notice that this star here has very little metal. It's kind of metal poor, as we say. The star right above it is metal rich. So this star on the bottom of the screen is what we would refer to as a population 2 star. It's a member of the previous generation. It was born into a universe with far fewer or far less, far smaller ratios of heavy elements. This baby star here is a newborn, and this star was born recently, and so it's, again, been born into a heavily enriched universe. So that star is even more enriched than our sun is. Any questions about that? I think that's a very interesting topic. Often people will ask me if there's going to be another generation of stars. Sure, but that will take a long time. And people ask me what we'll call it. I suppose we could call it population 0. Be aware that you live in a healthy galaxy. The Milky Way galaxy is actually filled with stellar nurseries where brand new baby stars are being born before our very eyes. Something to think about. Go back to 0. Before I move on, any questions about the spectra thing? Watch this. I'm going to go over to the left of the screen here. Let me get my head out of the way there. I'm going to zoom in again. Go to the very left. And I'm going to go up and down. Notice that all the stars have something right here. Well, that's the hydrogen alpha line, isn't it? It doesn't surprise me that all the stars have that line because all stars are made of almost entirely hydrogen and everything else is rare by comparison. I wonder what this line is. They seem to all have that too, or at least most of them do. Interesting. I wonder if that could be another famous and highly abundant element in the cosmos. What could I be talking about? Oh yes, look at that. Helium. See that, guys? So, all stars are made of hydrogen. Most have lots of helium as well. And then some, very young ones, have lots of other stuff. But for the most part, stars are dominated by hydrogen and helium. By the way, it's not just stars that are mostly hydrogen and helium. We'll talk about that more in a few minutes. Questions about that? All right, I'm back again. How are generations defined? So like I was mentioning, we determine the generation by how metal-rich a star is. That metallicity tells us how rich the universe was when the star was born. It tells us what it was able to inherit. So a very rich star will be young and a member of the youngest generation, in fact, and an extremely poor star will be a member of population 2 or 3. 3 was the first generation, those born immediately after the Big Bang. Not surprisingly, population 3 stars are very difficult to study. And one of the important things the new James Webb telescope will do when it gets launched, hopefully at the end of this year, will be able to study the first stars. It will be able to study in infrared light the spectra of the very, very first stars in the very earliest universe, in extraordinarily distant galaxies. It will be able to study galaxies only a few 100 million years old. In some cases, maybe even just a few million years old. Galaxies that were formed immediately after the Big Bang, filled with population 3 stars, those ancient metal-poor stars. Good question. The alpha line was discovered in 1885. Yeah, that's right. And around that same time, we also discovered helium. And the term, or the name helium, invokes the god Helios, the sun god, because they discovered helium in the spectra of the sun before we found it on Earth. I think that's a great story. We found helium on the sun before we found it here on Earth by studying the sun's light and finding this mysterious line that we didn't find on Earth. It didn't seem to correspond to the materials we were using on Earth. Of course, as you guys know, helium is not common on Earth's surface because it floats away. So the only time we really have good access to it is when we dig it up from captured underground sinks. And we found several of those and, of course, have unfortunately squandered them. We are getting pretty low on helium on this planet as a result. Yeah, that's good. So we just talked about how we're able to observe the sun with such fidelity. And now we're going to identify some features. I'm going to let that video run there while I'm going to think about maybe using some different ones just for fun, because I always use this video and I'm trying to mix it up. All right, here's a different video. This was shot on September of 2016, an unusually busy day on the sun in 2016. Again, this is not a picture, this is video. Notice that it's wiggling and jiggling. Before I move on, let's see if you guys know. What is causing that motion? You guys see the wiggling. What's going on? What's causing that? What do you think? I want you to answer this one. This is an important question. Atmosphere, very good. Where? Whose atmosphere? What atmosphere? Where? Which atmosphere? Ours, good, that's right. So it's difficult to observe the sun. You know it's out in broad daylight, of course, and you're looking through warm or hot air. In fact, September is pretty warm. And so you're looking through turbulent atmosphere, unfortunately. And so all that wiggling and wobbling you see is Earth's atmosphere distorting rays of light chaotically. As I've said before in other shows, the Earth's atmosphere is not our friend. And that's why some of the best solar astronomy is actually done in space. And we're going to be using some footage in a few minutes from space telescopes designed to look at the sun, like the famous SDO and the famous Parker solar probe, which you may have heard is hurtling towards the sun. Yeah. So let's go over some features. These things that you think are flares that are not flares are called prominences, like I said earlier. These ones have kind of random shapes. And by the way, they ain't small. To give you some context of how tall these are, I want to show you a size comparison. You might enjoy this graphic. So 1,300 planet Earths would fit inside Jupiter, and about 1,000 Jupiters would fit inside the sun. So that means about 1.3 million Earths would fit inside the sun, in case you weren't sure how big the sun was. That means that the Earth will appear as a speck when you look at the sun up close. So be aware that the Earth would be slightly larger than that sunspot right there. That means that these structures, these prominences, are significantly larger than our planet. They would tower over the Earth. Think about that. Okay, so like so many things, these are not permanent structures. Talk about why they form in a second, but prominences, and then these dark lines, filaments. Filaments have a different name, but they are the same phenomenon. Filaments are simply prominences that are facing towards you because of perspective. So these are one and the same in terms of what type of structure they are. Now let's talk about what's going on here. Prominences and filaments are solar plasma, hydrogen and helium excited to an ionized state, which is highly charged, and it is trapped within powerful electromagnetic fields, which exist at the surface of the sun, within the sun, and far beyond the sun. The sun is incredibly complex when it comes to electromagnetism, and not only are the fields complex in structure, they are also chaotic in their motion, and again, temporary. The magnetic fields that create these surface structures are always changing, and as a result, all of these surface structures are temporary. Sometimes you'll see them come and go within a matter of minutes or hours, sometimes days, sometimes weeks. Very rarely months, but never years. We never see these structures persist for that long. But sometimes on a rare occasion, we'll see something last for months. Any questions about that? Someone asked, how would it look through without the atmosphere? It would look better. Without Earth's atmosphere, the image would be sharper, the image would wiggle less, and more importantly, we would be able to observe more wavelengths. One of the other reasons that we use hydrogen alpha etalons is because the hydrogen alpha line does penetrate Earth's atmosphere fairly well, so we're able to observe it. But there are many interesting solar wavelengths which cannot be studied on Earth's surface, so you have to go to space, or perhaps an airplane if you want to study them? That's a good question. Okay, magnetic fields holding material above the surface are responsible for prominences and filaments. I'm going to show you how interesting those magnetic fields can be in a minute. But just be aware that these are electromagnetic phenomena. And this might disappoint you. Essentially everything that we see on the sun's surface is electromagnetic in nature. Some of you might be aware that something very interesting, very powerful is happening inside the sun's core, but that particular mechanism, which we're going to talk about in a few minutes, is not occurring on the surface or near the surface. Most of the features that we observe on the sun's surface are essentially window dressing. They are not really indicative of the sun's internal activity. They exist because of the magnetic fields, which exist for all kinds of reasons, which we're going to get to. The probe that is on its way, will it be able to... Oh, yeah, absolutely. So the Parker Solar Probe is already providing fantastic images of the sun. I might be able to provide some of those by the end of the show. Now, we talked about prominences and filaments. Let's talk about this bright spot and then this dim spot. Now, you already know what the dimmer spot is. Tell me. I'm just going to say it because I know you know. That's a sunspot. And as we discussed, that is cooler. But then right next to the sunspot, we see this plage, which is French for beach. And just so you know, there are no beaches on the sun. It may seem strange, but plages and sunspots are often associated with each other. You often see them together. And the reason I say that may seem strange is because they are essentially the opposite of things. I told you the surface is about 10,000 degrees. Sunspots can be cooler, 5,000 or 6,000. Plages can be well over 10,000. They can be 14,000 degrees. It may seem peculiar that you'd have opposite things near each other, but understand that these electromagnetic fields are going to attract material in such a way that it will be dredged up, or attract material in such a way that it will be dredged down. Now, there's something simple. I showed you this picture last week, a little grade school science for you. You can clearly see here the iron filings following the lines of electromagnetic flux. Imagine the solar plasma doing that. Imagine material being dredged up or being drawn down, depending on its polarity and the polarity of the magnetic field. So, these features are caused by electromagnetic fields, either increasing the rate of convection, which carries heat to the surface, or stymieing convection by dredging material down, upsetting that upward flow of energy. Also, the magnetic field is concentrating these solar ions into a relatively small cluster of areas, and that increases temperature as well for electrical reasons. Joule heating, that term we use for why things get hot when electricity flows through them. There's a little bit of that going on as well. So the surface material is actually being heated by electrical current flowing through it. Any questions about that? I'll let you ponder that for a second. Speaking of convection, different types of stars have different convection regimes. Our sun is what we refer to as an intermediate mass star. And you'll see that it has an inner radiative zone and an outer convective zone. But low mass stars like red dwarfs, they will be fully convective. And high mass stars like blue giants, they will actually have the opposite arrangement of the sun, where they have an inner convective zone and an outer radiative zone. By the way, these type of stars, because of that structure, shed mass at a tremendous rate of speed. These types of stars are known to have violent outflows of material that's being continuously ejected by the intense radiation pressure. In the case of our sun, it's not ejecting material as rapidly because of this inverted relationship between radiation and convection. You might already notice, and we're going to talk quite a little bit about this in a few minutes, that the energy source, so to speak, of the sun is in the middle, in the core region. Energy is coming out from within. We'll talk more about that in a few minutes. By the way, these different forms of convection also affect the life cycle of a star. A star begins to die when the balances between various forces that hold them up, so to speak, is upset. And those balances will be upset, among other things, by running out of fuel. And how convective a star is determines how well it will, or rather how efficiently it will use its fuel. You might be interested to know that a star like the Sun will use its fuel much more rapidly and less efficiently than a low-mass star like a red dwarf. As a result, red dwarfs live a lot longer. We'll talk more about that as we get closer to the end of the show. Does the Sun have any solidity at all? No, it's too hot. And if you think 10,000 degrees is hot, I got news for you. We're going to talk about that in a minute. But just so you know, the core region is millions of degrees. In fact, I'm going to give you an exact number in a few minutes. So yeah. Oh, Sun is a huge ball of heated gas, someone says. Well, it's not actually a gas. Because the Sun is so hot, it's actually in a state of plasma. This is one of the most common mistakes when we talk about stars. We talk about stars as though they were giant balls of burning gas. Not only are stars not gas, they're also not burning. The Sun is not on fire, and again, is in a plasma state, not a gaseous state. You might say, but Troy, hydrogen and helium are gases. Well, they are at room temperature. But the Sun is far too energetic to allow them to remain in their gaseous state. We're going to talk about that more in a minute. That's a good question. Oh, someone said plasma. Very good. We need some water. Let's see another question, and then I'm going to move on. I got more videos to show you. Okay, so I told you I'd show you the magnetic field, how crazy it is. Before I do, someone said the word plasma. Let me show you some footage from my plasma globe collection. I used this last week when we were talking about electromagnetism. It's certainly pertinent. So here we have a plasma globe. It's actually this one in my hand right here, with a custom mixture. It includes oxygen, which is intended to simulate the aurora borealis. By the way, the northern and southern lights are also a plasma phenomena. What we're dealing with here is gas that is no longer gas. It's been excited to a plasma state, in this case, by high voltage. In the case of the Sun, by high temperature. But either way, we have phase transition from gas to the next state of matter, plasma. Now, because plasma is comprised of ions, that means that the atoms are charged. The atoms are very angry. They don't want to be charged. They have too many or too few electrons. This makes them want to seek out other atoms to discharge into, sharing electrical charges. But because there's so much energy present, they can't do that. They remain ionized because of the external energy being, in this case, pumped in via electricity, or in the case of the Sun, again, via heat. By the way, brief color lessons here. All these colors are important, aren't they? They tell us what these materials are, like we talked about with spectroscopy a bit. You're going to see me pick up a light bulb in a minute. There it is. And it's full of neon. See that? I know it's full of neon because it's orangey red. You might recall that chart with a different spectra on it. The neon is being ionized, again, in this case, by high voltage, not by high temperature. Although, interestingly enough, the temperature of the neon, when I ionize it like that, is over 300,000 degrees Fahrenheit. Now, that might confuse you, because I told you the Sun's surface temperature is only 10,000 degrees, but this also has to do with how rarefied the material is. A given amount of energy can excite individual atoms to very, very high temperatures indeed, if there are not as many of them to go around. What I'm implying is the surface of the Sun is not very dense, and if you were to try to walk on the Sun, which would be very unwise, you would fall through it. And you'd fall quite a long way, actually, before you finally got stuck, so to speak, in a plasma gradient that was dense enough to hold you. Yeah, so the surface of the Sun is actually surprisingly low in density. It would measure as a vacuum if you were there. A very hot vacuum, though, because it's not really a vacuum. It's full of very angry hydrogen and helium nuclei. Questions about that? Oh, good. Someone might mention the nitrogen in the background. Actually, that's actually not nitrogen, though. That particular tube is hydrogen, actually. All right, so the Sun is in a state of plasma. And because of its enormous heat, tremendous quantities of electrical current are flowing through that plasma. You see, plasma is extremely conductive, like I said, because it is ionized. So if you, I talk about this a lot, the best example of that is lightning. If you've never thought about it before, lightning is plasma air. Here's some lightning over our old North Dome from the old facility. Lightning is the air itself converted from gas to plasma, which is ironic because air is considered an insulator, and yet once you've managed to ionize it, It's like you ran a wire across the sky made of metal, even silver. Silver is, as you know, very conductive, even more conductive than copper. The reason that tens of thousands of amps of electrical current can flow through a lightning bolt is because it is plasma. So in the case of the sun, you have lots of plasma, and that material is highly conductive, and trillions upon trillions upon trillions of amps of electrical current are flowing through it. Questions about that? Here is a picture of the sun's magnetic field on a given day in November of 2017. Question, do you think this chart or map of the sun's magnetic field is useful today? No, because like I said earlier, the magnetic field of the sun is ever changing. So all these field lines are long gone. Again, this was 2017. By the way, the sun is surrounded by, let's say, and I'm going to use the word very loosely, an atmosphere, which we refer to as the corona. The corona is thin, very tenuous plasma, hydrogen, and helium that is trapped in the magnetic field. Notice the shape of the solar corona agrees with the magnetic field. Isn't that fascinating? How is the field measured? Which field are we talking about? The individual, like the field lines on the sun? So some of them can be measured directly by satellites and probes. Some of them are inferred by observing the motion of solar plasma at the surface. So we can actually observe the motion of surface material on the sun and infer the structure of the magnetic fields. Oh, by the way, and also by observing the structure of the corona. Again, the corona also reveals this. That's a good question. So these are static images. Let me show you something a little more dynamic. Check this out. Look at that. Now, the rotation you're seeing here is not the sun's rotation. Of course, the sun does rotate. The rotation here is simply the model, the three-dimensional simulation being rotated so that you can see the entire sun. Here it is zoomed out. Complicated, isn't it? The reason it's so complicated is because the material of the sun is moving in complicated ways. It is the nature of plasma to be chaotic. You saw those videos of my plasma globes. Because plasma is charged, it tends to attract other plasma or repel other plasma. So you have material that can repel or attract itself. And this lends itself to complex motion. But that's just the plasma doing that. Then there's something else. The sun itself moves in non-uniform manner because of convection. So parts of the surface of the sun are moving at different rates than others, and this twists everything up. Someone asked, what are those bright colored spots? Those indicate regions of unusually strong magnetic field intensity at the surface. Oh, and by the way, those tend to be associated with sunspots. It takes a great deal of electromagnetic energy to stymie the convection of the sun. And so sunspots tend to be the sites of the strongest electromagnetic field disturbances. By the way, that's why sunspots get a bad rap. Sunspots are often implicated when people talk about radio interference or power grid disruption. Sunspots aren't doing anything. However, there is another solar phenomenon we haven't talked about yet, solar flares. Flares tend to occur at sunspots because that's where the magnetic fields are strongest. Solar flares occur because of magnetic fields suddenly failing and dumping their energy onto the surface, resulting in superheating, which causes a massive explosion. That's what solar flares are. So again, the reason flares tend to occur in sunspot areas is because that's where the fields are strongest, and that's also how sunspots get blamed for things. Someone asked, how does our sun's magnetic field compare to neighboring stars? Yeah, so the heliosphere of the sun is defined by the sun's magnetic field. I showed you this video last week. Other stars have these as well, and they're known as astrospheres. Some stars have weaker magnetic fields than the sun. Some stars have much, much stronger magnetic fields. Ironically, red dwarf stars, which are less powerful, smaller stars, often have extremely powerful and chaotic magnetic fields. This has to do with the way their fields get twisted up for a longer period of time. It also has to do with the fusion that powers them. We're going to get to that, being less even in its energy output. So yeah, there are stars with larger and some smaller astrospheres because their magnetic fields do vary. Yeah, so different stars do have different field strengths. That's a good question. Here's that image of a bow shock of a star plowing through the interstellar medium. And again, that's the star's magnetic field pushing interstellar hydrogen and helium out of the way, and it piles up in the front like that. Here's another one. And here's 4 more. These are all examples of stars making their electromagnetic fields known by the way they interact with the interstellar medium. You might have heard that Voyager 1 and 2, the famous probes, knew they had exited our solar system when they stopped detecting the sun's magnetic field. We define the domain of the sun and other stars by their electromagnetic influence. Good question. Does a supernova release energy? I think that might be a joke question because, oh my goodness, supernovas are among the most energetic phenomena in the cosmos. There are very few events more powerful than supernovas. And this is not, I'm not making this up. A supernova explosion in a single month can release as much energy as the sun will during its entire 10 billion year life cycle. And if that sounds impossible to you, understand that a supernova is so energetic that it's converting significant portions of the star's mass directly into energy. And so, yeah, it's absolutely mind-boggling the amount of energy that a supernova can release. And because they do that, they can do some extraordinary things, like synthesize heavy and exotic elements. You have supernova explosions to thank for some of the rarest heavy elements. So I'm not going to spend too much time on that in this show because that's actually a topic for another time, but that's a good question. And by the way, supernovas are the deaths of high-mass stars in the case of type 2 supernovas. And our sun will not do that. Our sun does not have enough mass. It lacks sufficient mass to produce enough compressive force during its collapse to explode as a type 2 supernova. So our sun will not blow up. It will die in about 5 billion years, but it will not explode. Aren't you relieved? Yes. Questions. These are, you know what? Lots of good questions tonight. Keep watching that. I'm going to go back to cosmic rays more damaging. So that's a good question. I'm glad you brought that up, actually. I've noticed very frequently. Let me bring up a solar video here. This is actually from the Solar Dynamics Observatory. So I'm going to let this run. Some very impressive footage here, including some footage of solar flares. So as I was saying, cosmic rays include particles and electrons from the sun. They also include particles and photons and electrons from outer space. And even though solar wind and the cosmic rays associated with it are damaging, indeed, believe it or not, cosmic rays from deep space can be far, 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 far more powerful than those measured from the sun, because the sun is not so violent of an object. There are phenomena in this universe that make the sun look absolutely cool and calm and weak by comparison. We have observed cosmic ray impacts on Earth that were so powerful that if you had been struck by one of them, you would have been killed. There was a famous event in the 1990s where a single proton struck Earth's upper atmosphere and released the equivalent energy of a Major League Baseball thrown at 90 miles per hour. And that may sound like not very much power, baseball. We're talking about a single proton doing that. Yeah, so we don't even know where cosmic rays that violently energetic come from. But they are bad news when it comes to space travel. They're one of the key dangers of human spaceflight. And we don't talk about that enough. We love to talk about food and water, growing potatoes in space and all that. But we like to neglect the fact that without the protection of a thick atmosphere above your head, cosmic rays are a serious danger. Yeah, that was a good tangent. You know what? I'm going to keep going on that tangent because I got a cool picture for you. So how many of you have taken a picture of a cosmic ray? Now, that may sound like a stupid question, but believe it or not, I bet at least one of you in this chat has accidentally done it, because it's very easy to do it accidentally. So when a cosmic ray strikes the upper atmosphere, it will destroy an atom. And that atom will create what we call an air shower of secondary particles that fly down to Earth's surface, and they can be detected, believe it or not. There's a cosmic ray impact on the sensor of my camera. As you can see, it triggered a number of blue and red pixels. Now, there doesn't seem to be any cosmic rays in this image, but if I zoom in, that's the one I just showed you. See that? Here's another one by the cell phone tower. Look. Zoom in here. That's a pretty strong one. Look how straight it is. And see it hit many pixels on its way through. Those are cosmic ray impacts, usually secondary rays. Yeah. Sometimes from the sun. In this case at night, probably not. But it can be from the sun. It could be from deep space. It depends. Thank you for the cosmic ray tangent. I do enjoy that topic. All right, now. Features We haven't talked about the most exciting one very much, solar flares. Here's what a solar flare looks like from Earth. As you can see, we have intense brightening. That's because the temperature is being increased by many orders of magnitude. And you might notice that that filament is escaping. That's because the magnetic field that held it has failed, and the material flies away, pushed by solar wind. It's important to understand, again, that even solar flares, these vast explosions, are the result of electromagnetic fields. In this case, fields that are failing. Any questions about that? What's this thing? This is an automotive ignition coil. I don't need to get my head out of the way. Just this primary terminal there, so I'll put my head back. Ignition coils in your car. They create a high voltage discharge. How do they do it? Powerful magnetic field is created by the primary coil by 12 volts in your car system. That magnetic field is suddenly cut. It fails, it collapses. By the way, it's cut by the ignition system, the points. And because the field collapses at great speed, it induces an energy much higher on the secondary coil. People will often tell you the voltage is increased because the secondary has more turns. That's partly true, but it's also due to the speed of the collapse. So one of the reasons that solar flares are so violent is because you're dealing with an enormous amount of electromagnetic energy being released very quickly. That's right. So Ed points out breaker points cut the field. That's right. Magnetic fields can store energy. People don't think of electromagnetic fields as a storage medium, but they actually are. And as I mentioned in a previous show, our technology can make use of that. Filtration, for example, you can filter a circuit using the ability of coils to store energy. So I just told you that all these phenomena on the sun's surface are caused by the same force of nature, electromagnetism. Before I move on from that, let me show you some fun videos. Here's a prominence. Let me slow that down. Let's see. That's a little better. I was very excited about this particular prominence, and I had to shoot it. This was also in September of 2017. And what I love about this is how textbook it is. This prominence looks exactly like they often do in the books. It has a nice looping structure, and the reason for that is, like we discussed, electromagnetic fields propagate in loops and arches, don't they? Like I said, the solar magnetic fields are often more complex, and you get wilder shapes. But this is a relatively neat and tidy one. What's interesting is you can see the motion is surprising. You seem to have some material going one way, some material going another. Let me zoom in a bit here. I'm going to speed it up. You can clearly see material going one way and then some material going another because of the polarity of the field and the charge of the plasma. Any questions about that? I don't think this one's zoomed. Yeah, I should have used this video. This one won't fade out like that. There you go. So I was very impressed. Now this is about, what was that? 2.5 hours of time lapse. So it took many hundreds of pictures and then stringed them together. Any questions about that? If the sun's magnetic field was more orderly, more uniform, then we wouldn't see so much electromagnetic activity on its surface. Speaking of which, I'm going to show you something. Hold that thought. I'm going to show you a picture of the sun, and I want you to notice something about its activity centers. This is a real image of the sun, but it is a composite image. So this is actually many hundreds of images taken by the Solar Dynamics Observatory, which is a famous space telescope that observes the sun continuously. And what you notice is there are bands of activity in the tropics, if you will. The solar tropics are these regions of high electromagnetic instability. We tend to see more activity at the tropics. Again, we don't really have tropics on the sun, I'm just using the word to help you understand. And that's because of motion being non-uniform. The sun does rotate, but it rotates in a surprising way. Let's see if anyone knows. Does anyone here know how long it takes the sun to rotate? And if you don't know, guess. Someone throw a guess. How long does it take the sun to rotate? Here it is spinning for you. This is, of course, sped up quite a bit. Oh, interesting question. He says, what part? 30 years. Oh, no. 25 days, very good, that's right. So it takes the sun 25 days to rotate. However, when we regurgitate that little trivia factoid about the 25-day rotation rate, we're being very specific because we're talking about the sun's equator. In fact, the sun's poles rotate between 27 and 32 days. What? This means the sun is literally churning and stirring and mixing as it twists itself up. The sun does not rotate uniformly. How can this be? Because, again, it is not a solid object. It is a giant ball of plasma. Very angry, agitated plasma that is hot and undergoing complex convection at multiple layers beneath. So because the sun's equator spins slower than the rest of it, you're going to get turbulence in the, again, air quotes, tropics. And you get these activity zones. Isn't that interesting? Questions so far? Twisted fluid, I like that. So it's not actually fluid, but it does behave like one, so we can use that term. This type of plasma is known as an electromagnetohydrodynamic fluid because it acts like a fluid. It's not actually a fluid, but it behaves like one because it is charged. Questions about that? Let's go back to the exciting spinning video. This is about 1 year in 6 minutes. So that's to give you some idea of the rate that we're seeing here. Like I said earlier, this was shot by a famous thingamajig, the SDO. This is the Solar Dynamics Observatory, which was launched about 11 years ago, and it continues to orbit. And it continues, Earth, by the way, it orbits the Earth. And it continuously images the sun in multiple wavelengths. All of them ultraviolet, by the way. These are false colors you're seeing in these videos because these are not visible wavelengths. By the way, that's something we cannot do on Earth. We cannot observe the sun in ultraviolet wavelengths because of the atmosphere absorbing or scattering those wavelengths. Questions about that? So, some of you might be aware of the fact that the sun has an activity cycle. This is often referred to as the sunspot cycle. I don't like using that term because it's not actually the sunspots that are cycling. It's the sun's magnetic field. Every 11 years, the sun's magnetic field goes crazy. But it's not actually just randomly going crazy. It's actually flipping. Every 11 years, the sun's north and south do this. Every 11 years. And sometimes it does it chaotically. For example, for a while there, recently, about 8 years ago, the sun had 2 south poles. Amazing. Weird. It's because the north poles were stuck on the inside. Yeah. So every 11 years, we see an activity increase, and then it wanes. Notice that we're on a downward trend. We're seeing a decrease after decrease after decrease of solar activity. However, there have been little spikes or hotspots. Notice back here in the late 1980s, this spike was associated with a very powerful solar flare that knocked out power in the northeast United States and Canada because a geomagnetic storm, which entails Earth's magnetic field being disrupted by high-energy particles, actually induced voltages on power lines, causing failures. It also destroyed satellites. So that's a lesson we're learning. Notice that, contrary to nonsense telling you, people say the sun's getting hotter, as you can see, no, it's not getting more active. It may, in about 1 billion years or so, we expect the sun's activity to increase as the fusion that powers it moves closer to the surface. Please don't worry about this. By the way, the sun is starting to wake up. We're starting to see the next solar cycle begin, so I'm looking forward to getting some good videos and pictures of exciting phenomena. Any questions about that? Now, speaking of which, check it out. This was on January 2nd, so just a few days ago. So here's some footage. Did you see that cloud of darkness as it kind of flew away from the sun just now? There goes another one. See that? Let me slow it down a little bit. Move forward a bit. Keep watching the screen right around here. See that? The cloud there, left? So that filament was suddenly released by a magnetic field collapsing. This indicates instability. So yeah, we're starting to see the sun wake up, and we're seeing that all of the new phenomena on the sun's surface are the opposite polarity from the previous solar cycle. That's how we know we're entering the next solar max. And by the way, that's what we call it. The solar maximum is when the sun's field goes crazy and flips. Solar minima is when it's calm and quiet. I will tell you that solar minima is very boring when it comes to Actually, the wavelength's right there. It mentions 304 angstroms, and I think that's what that is. But it's an ultraviolet spectrum, in case you were wondering. Speaking of which, here's some more ultraviolet data. Now, this is only 8 frames, so let me go slow. As you can see, right here, we have a filament. The magnetic field suddenly collapses, and you can see the material flying away. See that? Yes, these are all false colors because you cannot see ultraviolet light. And I want to repeat, this is the kind of work you can do in space because without the Earth's atmosphere, UV can be studied. Ultraviolet is desirable for solar astronomy because it tends to accentuate the high energy regions on the surface. Because obviously it has to be more energetic if it emits more UV rays, because UV is a higher energy wavelength than, for example, visible light, and certainly more high energy than infrared. Yeah. Now, let me show you some exciting video. We're going to go back to this. Why every 11 years? We don't know why it's 11 years, and it probably will not always be 11 years. In fact, it isn't. It's not exact. And this has to do with resonance. Any electromagnetic system is capable of storing energy and reacting to change. So we have fields that are pushing against other fields and setting up harmonics. By the way, we see this similar in planets too. Remember we talked a little bit about magnetic fields of other planets last week. It also has to do with literally the sun spinning and spinning and causing these field lines to twist and twist and twist and twist until they need to break. And this leads to a cascade of changes. You could think of these magnetic fields as a big rubber band, and when one snaps, the other ones change in their tension as well. It's quite complicated. Could these phenomena be observed in visible light from space? Oh, sure, especially things like solar flares, where the sun's surface brightness can increase significantly. In fact, in history, there have been moments where solar flares on Earth were detected. Actually, here's a video I shot recently, or not recently, about 6 years ago, and I showed you this earlier. This brightening, although you wouldn't have seen it with the naked eye, was certainly measurable, and you can see that in the camera sensor actually overexposed. You can see that the solar flare is causing the camera threshold to be exceeded, and it just blows out white. Yeah. Oh, interesting. External forces are all internal. So all internal. There's not. Although it is true that the planets can tug on the sun's surface a bit and might contribute to the twisting a little bit, but most of these are internal mechanisms. On that subject, we should move on to the final topic. And by the way, we really flew through the time tonight. It is true these solar shows tend to be long, but I was hoping I could get it condensed enough to stay under an hour. But we still have to talk about the most important thing, and that is what the sun is truly doing. So let's see how quickly we can do it. I told you that the sun is in a plasma state, and that's what leads to all these electromagnetic phenomena on the surface. And I told you the sun is hot. Let me show you some cool video footage again. Watch this. Let me back up a bit. I'm going to get my head out of the way. Watch the upper left corner of the screen here. That was a solar flare. See that? Notice some of the material gets sucked back by either magnetism or gravity or both. By the way, I forgot to mention that the prominences, which look different in this wavelength, they don't want to be there. This material does not want to hover above the surface. It wants to either escape or it wants to fall back. Here's another one. Watch. Boom. See that? That's a big solar flare. See the material leaving? Let's watch that again. Let me jump ahead a bit. I'm going to find a good spot for you. Let me see here. Look at all that activity. Notice the motion. Notice how dynamic all these structures are. This is obviously time-lapse. It's being sped up about 12 minutes per second is a time ratio we often see in this video. This was all shot in 2013, and that's not a coincidence. That was the last solar max. Go ahead a bit here. Watch this. Watch the top here. Watch this. Oh no. So after a solar flare, what happens to the material that escapes? So some of it falls back, as you can see happening here in the video, and some of it achieves escape velocity and never returns. Much of that material is moving well over 2 million miles per hour, which is twice the necessary escape velocity from the solar surface. That material will never leave it. It goes out and runs up against the inner edge of the bow shock that we talked about earlier, becomes part of the interstellar medium. By the way, it also runs into planets and strips them of their atmospheres. We've talked about the damaging effects of solar wind in multiple previous shows. And if a large clunk of material strikes us directly, oh, by the way, good timing. Watch this. I'm going to stop talking for a second. Watch that big filament there. Look at that. Very impressive solar flare. If a big glob of material like that, which is referred to as a coronal mass ejection, were to strike our planet, it can touch off an unusually powerful electromagnetic field disruption, a geomagnetic storm of great magnitude, which can, like I mentioned earlier, damage infrastructure, destroy satellites, power grids, things like that. The good news is that we are not going to be caught unawares this time. If it ever happens again, we have early warning. And there are things we can do to prevent damage, like shut down the power grid prematurely or ahead of time, to tell satellites to enter their shutdown or sleep modes, things like that. So we are much better at protecting our planet from solar activity than we used to be. Because we learned our lesson the hard way back in 1989, like I mentioned, when that very expensive solar flare damaged our planet. Damaged our gizmos anyway, our gadgets. Okay, now. So that's you know what, that's a great question because it segues into a very important tangent. The sun does indeed rotate in a prograde manner, which is an agreement not only with the prograde motion of all the other rotations in our solar system, all the other rotating bodies, but also the orbital direction as well. So planets both rotate and revolve in a prograde manner with a very short list of exceptions. Planet Venus essentially spins backwards, although she orbits in the correct direction. Essentially, Venus is upside down. There's also a number of moons and other minor bodies which go backwards. Most famously, Neptune's moon Triton, not Titan, Triton, orbits the planet backwards, so not prograde. But the majority of objects in our solar system orbit and rotate in a prograde manner. Now, this is profound because it speaks to the formation of our solar system. Let me show you what I'm talking about. So, this is a gorgeous real picture of the R136 star cluster in the Tarantula Nebula. The Tarantula Nebula is a nebula in the Large Magellanic Cloud, about 165,000 light years from Earth. All those blue stars you see are baby stars, brand new, newborn stars. Enormously hot and energetic, as stars tend to be when they're born. And I can move around this image and see, move around this image and see other structures. For example, watch this. I'm going to find some what we call Herbig-Haro objects and Bach globules. So these blobs, these are regions where static Klingon gravity has caused the nebula to collapse. By the way, these are huge clouds of gas and dust with heavy element impurities like we talked about at the beginning of the show. And the material has condensed enough to become opaque. Within these blobs are forming baby protostars. As the stars become energetic, they start to shed material, and we get objects like this. These are called Herbig-Haro objects, and these streams of material are actually being blasted out by these young protostars as they begin fusing, as they start to turn on at the beginning of their life cycles. So not only do we see this cluster filled with baby stars, and we see a nebula full of, look at that, more of them, Bach globules and Herbig-Haro objects. We see both things continuing. So we have both stars that are already born and stars being born. Now, let's look at an artist's impression really quick of what our solar system might have looked like about 4.5 billion years ago. Solar systems, star systems collapse and rotate, and as they get smaller, they spin up. Their rotational velocity increases due to the conservation of angular momentum, just like a figure skater pulling in her arms. As this blob of rotating material shrinks, it flattens into a disk because we have two actors vying for the material. You have a centripetal actor, in this case gravity, which pulls inward towards the baby sun, and centrifugal force, in this case inertia, pulling away. The majority of material in the star system remains either in the disk or falls into the middle and becomes part of the sun. All that material is moving in the same direction, that prograde direction. And so any planets that form within it will inherit that inertia. Any questions about that? I have a picture from my show last week. It's kind of important about that. Let me show you really quick. Remember this? This is a real picture. This is not a drawing. The thing I just showed you was a drawing, but this is a real image of a baby star system called HL Tauri. And this is not only a very high-resolution image of a protoplanetary disk. Not only do we see a baby star forming in the middle, we also see grooves being carved out by baby planets. And again, they will inherit and retain the prograde motion of the entire disk. And of course, so will the star forming in the middle. You know, it's very difficult to perturb a planet. Something that weighs quadrillions of tons and is moving at tens of thousands of miles per hour will not be easily shifted off its course. That's why they retain that motion. Good question. That was a helpful tangent. And it gets me close to the end of the show, actually. One last thing to talk about, and that is essentially what powers a star. I apologize for being over time, but I think this will be... when do stars create planets? Stars do not create planets. Planets form around stars more like siblings. I know we think of stars as the parent of a star system because they're heavier, but the planets form with the star. We've learned that this process is surprisingly fast. Planetary accretion plays out in only a few tens of millions of years. When you think about the lifespan of a star, that's not a long time. So there are no objects in a given star system that are significantly different in age. Everything's going to have a similar age because they formed around the same time. So again, it's more like they're siblings than children, so to speak. So we talked about the fact that the sun is hot, and that's what makes it a plasma and so electromagnetically interesting. But we haven't talked about why it's hot. This surprisingly simple question has a surprisingly profound implication because the answer also tells us something else. Telling me why the sun is hot also tells us why it is a star, because the source of the sun's heat is the defining characteristic of starhood. So to finish the show, this is our final topic. Why are stars hot? And I'm going to tell you right now, they're not on fire. They're not burning. So the thing about Venus being upside down, we don't know. It could have been struck by something. It's a mystery. Most likely, I mean, it's almost certain that Venus formed with the other planets, but we don't know why it's upside down, so to speak. It does go the right direction, though. She does orbit in the right direction. Fusion, good. Thermonuclear fusion of at least hydrogen is the defining characteristic of stars. The reason I say at least hydrogen is because there are stars that can do far more than that. Now, humans have achieved hydrogen fusion with frightening devices. This is Castle Romeo, a famous hydrogen bomb test back in the 50s, I believe. This is a fusion device. This is Castle Bravo, the most powerful hydrogen bomb detonated by the United States, 15 megatons. Not the most powerful in history. The Soviet Union blew up the famous Tsar Bomba, which was 50 megatons. But these instruments of destruction employ the same mechanism that heats the sun, thermonuclear fusion. Not to be confused with fission. Fission versus fusion, easy to remember because fusion is a literal term which means combining things, where fission is destroying things. In the case of fission in weapons, we use plutonium and uranium, which are inherently unstable radioactive nuclei. They want to be destroyed, and so they are easily broken or shattered by bombarding them with neutrons. Fusion is much more difficult because it doesn't want to happen. Atoms do not want to go together. Atoms naturally repel each other. Because of that force of nature, we constantly talk about electromagnetism. All atomic nuclei have a positive bias because all atomic nuclei contain protons. The electrons are inconsequential in this context because the energy levels are so great. So we're just talking about protons and neutrons. Neutrons have no charge. Protons have a positive charge. To get atoms close enough that they unite via what is known as the strong nuclear interaction, which is one of the most important forces of nature, also known as the strong force, you have to find a way to overcome their repulsion. Stars apply the force necessary for fusion via heat, hence the term thermonuclear fusion. Tremendous heat is required. By the way, it's not a small amount of heat. It's 22 million degrees Fahrenheit, give or take. It's pretty hot. Good news for us. The sun's core temperature is 27 million degrees Fahrenheit, so more than hot enough to not only start, but sustain the thermonuclear fusion of hydrogen. I have more to say about that, but are there any questions so far? I don't like to rush so much, but I do want to get done in a reasonable amount of time. 27 million degrees Fahrenheit is more than hot enough to maintain the fusion of hydrogen. Let me show you something really quick. I'm going to give you an oversimplified example of what we're talking about. This cartoon explains everything. Yeah, of course, this is oversimplified, but I wanted you to see the word thermo for heat, nuclear, because we're talking about nuclear particles, not chemical reactions. Fusion, combining, in this case, we're combining hydrogen to synthesize helium. So the sun is creating helium, slowly converting itself into it. It is also emitting tremendous amounts of light in the process, and that light occurs because of tremendous energy in the form of heat and gamma radiation, which excites the particles around it. That enormous heat at the center works its way up to the surface, and that's where we get those convection profiles like we talked about earlier. Now, again, we are oversimplifying things a bit here. But I just told you something confusing. I told you the sun is hot because of fusion, and then I also told you, almost in the same breath, that the sun is fusing because it's hot. That sounds like circular reasoning. It sounds like a chicken and the egg. But of course it's not, because we know what comes first. A star is born when the core temperature becomes high enough to initiate fusion. So to end the show, can someone tell me, where does the heat come from? What is the source of heat that allows a star to begin its life? Does anyone know? While you're waiting, I'm going to get the chat back open here. Can someone tell me? Ah, very good. Someone's asking it. I don't know. You tell me. What is the source of the enormous heat that starts a star on its journey? Where does the heat come from, guys? This is profoundly important. Pressure? Ooh, gravity? Ooh. Those are different answers, but they're both correct answers. Supernova? No, not supernova. Pressure of mass. Oh, good. Yes, good. Very good, you got it. So if you think of a diesel engine, diesel engines have no spark plugs. They create the heat for explosions with pressure. You guys know that pressure equals temperature, because the more pressure you have, the more atoms and molecules are running into each other. So it is indeed pressure that creates the temperature necessary for a star to begin its life. But where does the pressure come from? Someone already told me. Where does the pressure come from? See if you know. The answer is already there. What is the source of the pressure? Gravity, very good. And why is the gravity so intense? Why do stars experience such intense gravity? If you can answer this, you know how stars work. Mass, very good. Stars are extraordinarily massive objects. Our sun has 333,000, I'm going to repeat that number just so it's clear, 333,000 times the mass of Earth. It's a lot of material, which is remarkable when you consider that all that weight is comprised almost entirely of hydrogen and helium, which are considered, quote, light materials. But with enough of anything, it can have tremendous weight. So a star crushing down under its own weight due to its tremendous mass, that's what enables it to sustain thermonuclear fusion. Now, I'm going to quiz you. I'm going to show you a picture of a famous thing that you should hopefully be able to identify readily. What's this? Please don't get this wrong. What are you looking at here? I'm just going to tell you because I know you know. This is a model or a drawing of our solar system. Now, what's wrong with it? Please don't get this wrong. What is wrong with this picture? Anybody? What do you think? Distance, right, thank you. If this was distance accurate, we'd be in big trouble. Everybody would be consumed by the sun and destroyed in the process while we were being consumed because of the heat. So this is not distance scale accurate, of course, but what is correct? The size. This is size scale accurate. Notice mighty Jupiter, king of planets, bigger than the rest. Oh, there's little Earth. So Mercury, Venus, Earth, and Mars, these are the terrestrial planets, the rocky planets. Jupiter and Saturn, the gas giants. These two are also made of gas, sometimes referred to as the gas giants, also referred to as the ice giants, Uranus and Neptune, because they also have a lot of volatile compounds, including ices. But these four bodies, Jupiter, Saturn, Uranus, and Neptune, are mostly hydrogen and helium, exactly like a star and exactly like the rest of the universe. I remind you, the universe is mostly hydrogen and helium. So, here's the quiz. Somebody tell me, if Jupiter, let's pick on him, Jupiter. If Jupiter is exactly the same thing as the sun, the same material, hydrogen and helium, and it is, why is Jupiter not a star? If you guys can tell me why Jupiter is not a star, you understand how stars work. Go ahead. Someone tell me. Why is Jupiter not a star? Good. Not massive enough to experience enough gravity, to create enough pressure, to create enough heat, to undergo thermonuclear fusion. So, backwards. Jupiter is not fusing because his core temperature is not high enough, because the pressure is insufficient, because the gravity is insufficient, because it doesn't have enough mass. And that is the only thing between him and starhood, and same with Saturn, mass. If these bodies had become more massive, they might have had a shot. However, even though Jupiter is impressively massive, he's nowhere near starhood. And by the way, when I say impressively massive, listen to this. Someone just pointed out that the sun took its mass. That's correct. If you learn one thing tonight, learn this. The sun contains an extraordinary 99.86% of all the mass in our solar system. Think about that. 99.86% of the mass of our solar system is the sun, which is, again, amazing when you consider that that is hydrogen and helium. Again, quote, lightweight elements, unquote. That means that 0.14% accounts for all the planets, all the comets, all the asteroids, all the dwarf planets, etc., etc. Incredibly, mighty Jupiter, king of planets, contains 70% of that. So 70% of what is not the sun is one body, Jupiter. Saturn contains almost all of the rest. So our solar system is essentially three objects: the sun, Jupiter, and Saturn. Jupiter has more than twice the mass of all the other planets combined. Think about that. You might not believe me because Jupiter is not that much bigger than Saturn, but this is why it's important that you never conflate size and mass, because in space science, we see wild disparity between those two metrics. Some of the heaviest things in nature are the smallest. So, and some of you can have nebulas, that are light years across, or they can crush down into a single black hole that's an infinitesimal speck, which is mind-boggling beyond belief. So, the heavier something is, the better it is at crushing itself. And that's why even though Jupiter has about 3 times the mass of Saturn, it's not 3 times bigger. Any questions about that? Jupiter would have to gain about 75 times more mass in order for fusion to begin, in which case Jupiter would transform into what's known as an ultra-low mass red dwarf, the smallest type of star there is. So even if Jupiter did gain 75 times more mass, he would not be as powerful as a star, or as big as a star, as the sun. Questions? Are planets closest to a sun always smaller than those further away? No. So we have observed exoplanet systems with what we call, and there's a name, this is a class of object known as a hot Jupiter. Hot Jupiters are gas giants that orbit essentially too close to their parent star. And when I say too close, the intense heat and radiation pressure from the star is actually stripping them of atmosphere. So there are indeed inner solar system gas giants. However, they're in danger. There's a hypothetical type of planet known as a Chthonian planet, I believe, where it's the naked core of a gas giant which has been completely stripped away. There are a few candidate objects we've discovered, but we haven't proven that they exist. By the way, planets also migrate. We know that the gas giants started out their lives closer than they are to the sun than they are now. and they probably wreaked all sorts of havoc on their way out. Such massive bodies moving through the solar system would have definitely thrown off the orbits of less massive bodies for sure. Okay, so these are all good things. Let's finish it up by showing a picture of stars versus stars. Is there a reason? We just talked about that. So it has to do with mass and weight. So you're going to have heavier material coalesce near the star. That doesn't necessarily mean, like I said earlier, that all the planets are going to be terrestrial, though, because they might also collect a lot of gas. But it's simply that gas has trouble accreting near the star because the radiation is so intense. Let me show you that picture again, this drawing here. Notice how there's a void carved out near the star. That's because the radiation pressure is so intense near the star that gas has to be blown away. By the way, when a star turns on, when fusion begins, the accretion process turns off because the star stops collecting material via gravity and starts rejecting material via electromagnetism. Just the pressure of light itself can reject, for example, monoatomic hydrogen, which is extremely lightweight. So yeah, a star, when it's born, will carve out these voids, leaving the material that can stay close enough and not be blown away completely to form planets like we talked about. Good question. Let's see. So, I'm going to show you a picture to finish this. I use this picture a lot. Many of you have seen it. One of these stars is the sun. You can probably guess which one. Someone tell me. Which one is the sun? I'm just going to look at my cell phone while you answer this super simple question. What has been going on in my chat? Let's see. I see. Okay. What gives the forming solar system its angular momentum to start with? Which angular momentum? The rotational velocity? So everything in the universe spins a little bit. And that spinning is accentuated by collapse. As it gets smaller, it spins up. But everything in the universe spins. What's important to remember is that spin is completely random. Every star system in our galaxy is crooked. There is no up, because that process is fairly chaotic. For something to start spinning, all it has to do is receive a little more kinetic energy on one side versus the other, and it will start to rotate. Right, someone got it. So that small dot, that little speck over there, believe it or not, is the sun. Unbelievable. And these other stars are famous. The reason I wanted to show you this image is because I wanted to show you something that might blow your mind. The sun is a G2 yellow dwarf, not the smallest type of star, but as you can see, much smaller than some of these other ones. Rigel is a white giant. Aldebaran is a red giant. Betelgeuse and Antares are red supergiants. You might think that these two mighty supergiants have millions of times the mass of the sun, but they do not. For example, Antares has only 7.2 solar masses, so only 7 times the mass of the sun, and Betelgeuse only 11 solar masses. How could they be so much bigger then? Solar systems. That's funny. So, Betelgeuse, and by the way, before I answer, an object could not be that massive. Betelgeuse could not be millions of times the mass of the sun, because if it were that massive, it would instantly collapse into a black hole and become what we refer to as a direct collapse object. It would be too heavy to exist. Anyway, the reason that they're less dense is because they're being blown into a larger size by greater energy, because the more mass you have, the more gravity, pressure, and temperature, which drives faster nuclear fusion. Not only is the fusion of hydrogen more rapid and therefore more energetic, you also have enough energy to fuse heavier elements like helium into heavier ones. You have oxygen and carbon forming and neon forming. So supergiant stars not only fuse very rapidly due to incredible mass driving it, they can fuse more elements than just hydrogen. This dramatically accelerates their demise. You might be interested to learn that while our sun will live for 10 or 11 billion years, Betelgeuse and Antares will be lucky to live 10 million years, because they consume their fuel so rapidly. And like we mentioned about half an hour ago, when they die, they will not die quietly. They will explode as type 2 supernovas, and their cores will collapse into neutron stars. We talked about neutron stars last week during our magnet show. Our sun does not have sufficient energy to collapse into a neutron star, nor will it explode. It will form a beautiful type of object known as a planetary nebula. This is the outer layers of the star being shed as the star transitions to helium fusion at the end of its life. Meanwhile, the core collapses into a very compact object known as a white dwarf. This is a drawing that's supposedly of a neutron star, but I think it looks like a white dwarf might look. So there you go. This is my pretend drawing of a white dwarf. White dwarfs are incredibly compact, about the size of Earth. They contain the mass of much of the star's material in a much smaller volume, so they're incredibly dense and also very hot. This is the fate of our sun. Our sun will collapse into a white dwarf. And someone mentioned M57, that's what that beautiful nebula was. The outer material is ejected under radiation pressure, leaving behind this dead but very hot remnant. And I mentioned earlier in another show, white dwarfs will be the last hot things in the cosmos because they cool down at an extraordinarily slow rate. So they remain hot for millions of years, in fact billions of years. Our sun will form one of these one day at the end of its life cycle. These are the most common type of stellar remnant because most stars in the universe are low or intermediate mass. Questions? Yeah, there's a lot of nebulas like this, that's right. Now, we went way over time. We went half an hour over time, but we did literally go through a rapid-fire crash course of the entire sun. We started with surface activity, electromagnetic fields. And we ended with thermonuclear fusion. And we talked a little bit about birth and death of stars. So let's do 10 minutes of questions and answer, and then we'll wrap it up at 8:40. So 8:40. I hope you learned a few things. Go back to some video that we shot here at Goldendale Observatory. Notice the sun is much more red in this video than another one I showed you. This is one day different from this video. The color difference is caused by atmosphere. In that redder version, the sun was lower. It was set more, so we're looking for more air. Not helpful. I could have adjusted that, but I left it red so you could kind of see the effect. All right, 9 minutes left for questions and answers. Someone tell me. There must be something you're wondering. So someone asked about Doppler shift. Yes, I can, but in what context exactly were you hoping to learn about Doppler shift? It's true that Doppler shift, which is caused by relative motion, can actually cause the hydrogen alpha etalon that we talked about tonight to go out of tune because the wavelengths will be shifted a little bit outside of that 656 nanometer wavelength. So you have to tune for that. So these tend to be tunable. So since he asked about Doppler shift, let me show you. Photosphere or chromosphere has to do with the outer layers. Ed, feel free to explain that on the chat. I'm going to bring up the Doppler shift for this guy. So if you have an object that's stationary, I drew this. This object is emitting electromagnetic waves, and no matter where you are in this field, you will measure the same frequency. However, if you were to move the emitter, or you were to move in relation to it, you would notice an interesting phenomenon. The waves ahead of it, so to speak, are being compressed, and so their frequency will be artificially increased, but the waves tailing it will be stretched, and their frequency will be artificially dropped. This is where we get blue shift and red shift from. So here it is again, but now we have color-coded it. So I'm going to slow it down there. So, if something's speeding towards you, the frequency of its light will be artificially compressed towards the blue. If something's speeding away from you, it'll be stretched towards the red. This is extremely important in space science. It's one of the tools we can use to determine if something's speeding towards you or away from you and even how far away it is. We talked a bit about redshift in another show. The most redshifted objects in the cosmos are extremely, extremely, extremely far away, over 10 billion light years away. The reason their light is shifted so dramatically towards the red is because they're accelerating away from us at enormous speed due to cosmic expansion. The universe is increasing in size. Yeah. Yeah. So I'm not sure what you were hoping to accomplish with the Doppler shift, but that is Doppler shift in a nutshell. The most common example is the car horn. So if a car horn, a car drives by, so as the car, let's see, this is you. The car speeds towards you. The sound waves of its horn are compressed, makes it high pitched, and then once the car passes you, the sound waves are stretched, and we get the. So That's sound waves, not light. But interestingly enough, the concept applies either way. Imagine that. Do you think the universe is expanding in complexity at the same rate? While the universe is degenerating and that energy is being lost, mass being converted to energy, we are seeing greater complexity within that decay. So even though the universe is failing over time, you can see organized systems springing into existence spontaneously within it. For example, literally millions of baby star systems forming. Think about this. A star is a self-sustaining, self-regulating thermonuclear fusion reactor, and they are being born across the cosmos. And in a cosmos that is dying, so to speak, we still see the emergence of these extraordinarily complex and effective mechanisms spontaneously. So, yeah, I mean, the universe is atrophying, so to speak, but we can still see greater complexity within it. Just like you can make something, you can have a big box of stuff in a tool bin, or you could construct something out of it. You may have wasted some energy in the process, but you still made something useful. So, yeah. I try to avoid the word entropy because people have all kinds of ridiculous, nonsensical opinions about it. So I try to avoid that topic. So, mystical things. So, questions about anything we learned tonight? You guys had some good questions tonight. Go back to my video here. We have 4 minutes. So more density. Sure, you can have increases in density in a system that's expanding, sure. So let's talk about that. It's a very important topic. You hear about cosmic expansion or cosmic inflation, and people think that means that everything's flying away from everything else. That's not the case. Galaxy clusters are flying away from other galaxy clusters. So galaxies within our own local group will often be observed to have very little redshift or even substantial blue shift. The most famous example is Andromeda. Andromeda Galaxy is famously blue shifted because it's speeding towards us. Andromeda and the Milky Way Galaxy share a similar inertial reference frame because we're part of the same moving group. But if you were to look at galaxies far beyond the local group, you would see that we are receding away from them at great speed. So not everything in the universe is flying away from everything else. And that's because if bodies are close enough, their mutual gravitational attraction will overcome cosmic expansion, which is good news for us. The universe would be pretty depressing if everything was flying away from everything else. So yeah, even though galaxy clusters are doing that, individual galaxies and the objects within them are not. Good question. Oh, that's a good question. What focal length is this? This is about 850 millimeters. Unfortunately, that's not a very meaningful or useful answer to you because you don't know what size sensor I was using. In this case, it was a very small one. Yeah. I used a few different cameras for some of these, so it's hard for me to tell you what the field of view was on a given one, on a given image. And also, I did a little cropping and processing as well. So these aren't necessarily the most accurate representations of the field of view you would have got with an eyepiece, for example. Thank you. So let's see, we got 2 minutes. Answer asked earlier, I think, could we put out our sun's fusion by dumping a bunch of helium into it? Helium. Well, actually, that would increase the mass a bit, and it would actually increase its energy. By the way, speaking of that, people often ask ridiculous questions like, well, couldn't you dump a giant bucket of space water onto the sun and wouldn't that douse it? The thing is, that giant bucket of space water would dramatically increase the sun's mass. And by the way, water is hydrogen and oxygen. And so the sun would actually become empowered by that event. It would not be doused. I repeat, by the way, the sun is not on fire. The sun is not on fire. The sun is not on fire. It is not burning. However, you will sometimes hear scientists, astronomers, use the word burning when referring to what stars do. But that's because they know what they're talking about. When they use the word burning, they're actually referring shorthand to thermonuclear fusion. They're not talking about fire, which is a chemical reaction, the rapid oxidation of a material. The sun does have a bit of oxygen in it, but that is not the source of its power, not normal, ordinary fire. As you guys are probably aware, space is pretty empty and not a good place to start fires. Way back in the 1800s, which is really not that long ago when you think about it, there was a great mystery. They thought the sun was on fire, and so they were like, well, how is it getting oxygen to burn? There must be space air. And they had all these absurd hypotheses about where the sun's oxygen supply was coming from. Maybe it's full of its own internal oxidizers, and maybe it's made of coal. The sun is a giant ball of coal that's self-igniting somehow. No, It's not. It's not a giant ball of coal. Not combustion. Very good. Earth is pulled away from the water. All right, 1.5 minutes left. Would helium kill our sun? Let's keep exothermic versus endothermic. It's very highly exothermic. So the fusion reaction is releasing energy, net positive energy, yes. Let's see. Is there examples of tidal orbital moons? Yes, many. There are many orbital tidally locked moons. There are whole planets tidally locked to stars. Actually, amazing that. Imagine that. Not in our solar system, of course, but we now know of exoplanets where they have permanent day side and permanent night sides. We call them eyeball worlds because you'd have this ring around, essentially orthogonal to the equator, that would maybe be temperate. Who knows? So that's interesting. There are no tidally locked planets in our solar system to the sun, but there are tidally locked planets to their moons. Like, for example, former planet Pluto, he's tidally locked to Charon. Multiple moons of Jupiter are tidally locked to Jupiter. But yeah. All right, my friends. I hope we had fun. I hope we learned a few things. I apologize for going so long, although this is a dense topic. It's probably one of the more condensed topics we cover at Goldendale Observatory. It is possible to go over how our sun works in a fairly short amount of time. You don't have to go to a long, semester-length college course to learn how the sun works. Imagine that. Tell your friends, though. The next time you heard someone on a bus or a train or in the car say the sun is a giant ball of burning gas, you will shake them and say, no, the sun is a giant ball of plasma undergoing thermonuclear fusion. You fool! It's not their fault, though. They've been told this because of constant quotes from TV shows and movies, always referring to stars as giant balls of burning gas. Plasma hydrogen undergoing thermonuclear fusion. In the case of the sun, it will continue to do so for about 5 billion years. Please don't worry about the sun. You have much more immediate concerns, trust me. Especially this year. So. All right, guys, I'm going to go and tune in next week for whatever the show is. I actually forgot what it was. Let's see. Oh, hey, a fun topic. It's almost like we plan these things. So exoplanets. We're going to be talking about exoplanets, which are planets that orbit other stars. And I will be going over those tidally locked eyeball worlds that I mentioned earlier. All right, my friends, stay curious. If you had fun, if you liked things, please like the video. And if you want to see more things that you like, please subscribe to the Washington State Parks YouTube channel. And with that, remain safe. I am out.